Okay, thank you. Yeah, first let me thank the organizers for the opportunity to speak here, and it's a pleasure to come to Bedleva again and again and again. Maybe I should come more often because this tale for Eon I have drawn in the wrong direction. So, okay, so let me go to the talk. Not working. Yeah. So let me go sort of straightforward to the matter. So there is a result that most of you, or maybe all of you know very well. It's a Thurston topological characterization of rational functions. It's a sort of an important tool. When you have a sort of topological model for a rational function, modeling some post-critically finite dynamics, then this criterion tells you whether it's equivalent to an actual rational function. So it's quite important result. So you can sort of construct these topological models and decide whether you have the actual rational functions. So let me give a few comments about how we prove it. So the way to prove it is that first to take a look at some natural pullback map sigma, which is associated to F, and the maps between it acts on a Teichmüller space of the surface S2, where S2 is a two-sphere minus the post-critical set. I will tell you a bit. I'll give you the definition of the Teichmüller space a bit later. But now you can think of it as this a special finite dimensional metric space. So it turns out that the existence of this equivalent or combinatorial equivalent or Thurston equivalent rational function is the same as existence of the fixed point of this pullback map sigma. Next, what is easy to check is that sigma is weakly contracting. This means that it does not increase distances. So it's, of course, very natural to look for fixed points of sigma by considering iterations. But there's a big question whether it converges, but it's a natural setup to do this. So what do we do? We just investigate sigma and show that there is or there is no there is no fixed point. So I write just because that's basically where the main work is done. So but the first three lines are just sort of showing us the right direction how to deal with it. So now one can ask, how can one generalize this theory to the case where P is infinite? So, well, it turns out that there is no direct way to translate the proofs for the infinite dimensional settings because the things are too much different. For example, even on the way of the definition, or even on the side of the definition, sigma would be no longer a map acting on some fixed Teichmüller space. It might be a map between different Teichmüller spaces. Because if you have infinitely many marked points, then in principle, you have uncountably many different Teichmüller spaces. Okay, so we would like to focus maybe on the simplest case when P has only one accumulation point. Let us agree that this is infinity. And then the natural cases to consider are polynomials with escaping critical points, with all escaping critical points, and transcendental functions of finite type with escaping singular values. So here is a reminder for you what is a singular value of a finite type transcendental entire function, it's a union of critical values and asymptotic values, and the asymptotic value is defined here. So you just have a curve to infinity such that the values of the function along this curve they converge to your asymptotic value. Well, the simplest example is, of course, the exponential. And for the exponential, the set of singular values is 0 and infinity. So next, by slight abuse of notation, when I talk about singular values, I speak only about finite singular values, and I drop infinity just because it's a special point for us. So we imply that it's always there. It's always an asymptotic value. So the main motivation why we want to do this and to study this this Thurston iteration with infinite set of marked points is that we want to understand the parameter space and the spaces near the escaping parameters. So very naive and basic example, but which still can serve as a motivation, is that if we study a set of escaping parameters for the quadratic polynomials, then we sort of can understand better the boundary of the Mandelbrot set by moving towards it from outside of the Mandelbrot set. So yeah, so what is a parameter space for us? So if we have a transcendental entire function from Speiser classes that's of finite type, then we say that G is in the same parameter space if the entire function G is the same parameter space if these two functions are semi-conjugate by quasi-conformal maps. So in principle, the first map phi is can be used to sort of move the singular values somehow in the plane, and then the map C is basically the straightening map which integrates the pulled back Beltrami differential. Okay, so far so good. So in principle, for the parameter spaces, one could also consider different quotients by, for example, conjugacy by affine maps. But for us, let us live with this definition. It's quite okay for our purposes. So yeah, so so if we want to do this Thurston iteration for transcendental entire function, and especially for escaping singular dynamics, we could just take, as in the classical theorem, in Thurston's theorem, a topological branch covering and try to work with it. But again, there are problems even on the level of the definition. So maybe another good approach is just to take a quasi-regular maps, which is a composition of F naught, which from Speiser class with some quasi-conformal map. And in principle, this should give us most types of the combinatorics, partially due to this result of Lasserempe, which says that if F and G, even it's true even for bounded type functions, if they are in the same parameter space, then they are quasi-conformally conjugate near infinity on the escaping set, and even more generally on the set of points which sort of stay in this neighborhood under the iteration. Okay, so but before moving further, let me just define the Teichmüller space for you. So there are different definitions are possible, but this one is most suitable for us. So the Teichmüller space or TP of the Riemann surface C minus P. So we implicitly assume that P is closed, or if it's not closed at some point, you can take the closure of P. So is a set of quasi-conformal self-homeomorphism C modular postcomposition with an affine map and isotopy relative to the closure of P. So So, and what do we need to know is that equipped with a Teichmüller distance, the Teichmüller space is a complete metric space. So here is the definition of the metric of this metric, but I think we won't need it very much in this talk. Okay, so using this quasi-regular map, it's very easy to define the Thurston pullback map. It's defined by the following diagram. So the simplest thing is to say, for example, take phi, let phi be a quasi-conformal map, and then consider its Beltrami differential and pull it back via f, which is quasi-regular map. So we can do it, and then we integrate the Beltrami differential upstairs and obtain some map, quasi-conformal map phi tilde, such that the results in map G is entire. So, and then we assign that in the on the level of equivalence classes that the image of the isotopic class of phi is the isotopic class of phi tilde. It's quite easy to check that this is well defined on the level of isotopic classes.
You need just composition of I and F.
I and F,
not pullback in the graph. You don't have the right arrow, which is a posteriori.
This one we don't have. We get it after we integrate
linguistic delivery. It's perturbed by
yes. It's a quasi-regular map, so we can integrate the Beltrami differential living here, and then obtain by the measurable Riemann mapping theorem some map phi tilde. Okay, and so for the exponential family, the map G can be recovered quite easily. It's e to z plus phi to the A1, where A1 is our singular value of the map F. So in principle, one has a concrete formula to compute it. It's not even possible to recover it easily because you don't know which exactly branch of the logarithm you need to take, but it's at least something. But the goal of this talk is to present you some families of functions for which you don't need the explicit formulas to do this Thurston iteration and to derive the existence of a fixed point of sigma. So it just for illustration. Okay, so so we want to prove the following sort of meta statement. So if the sigma map associated with the constructed quasi-regular model map F, which is composition of lambda with F naught, has a fixed point. So how do we do this? So maybe it's partially because of insights for the analogous constructions for the exponential or the polynomial of exponential. We could construct a compact subset CP in the Teichmüller space. It's invariant under sigma and proves that the restriction of sigma on the CP is strictly contracting. Then basically by the Banach fixed point theorem, there would follow the existence of a fixed point. However, so well, this strict contraction part usually works relatively easy because we have the following result is that if we pull back to asymptotically conformal isotopic classes, I don't define for you what exactly is asymptotic conformal. It's not needed for this talk. Then that so is there asymptotically conformal? Then the distance between sigma phi and sigma psi, the Teichmüller distance, is smaller than between phi and psi. But it turns out that usually when one constructs this compact invariant subset, then you obtain it in such a way that your elements turn out to be asymptotically conformal or can be upgraded to be asymptotically conformal. So the main part is just to construct this compact subset. So we need to focus on compactness. So next in the talk, we would be discussing how to construct this compact invariant subsets in the Teichmüller space or in the extended Teichmüller space in a way. Okay, so far this was an old story with old proofs with all old proofs. Now we can finally move to the new stuff. To define the function, the general given not by formulas but somehow conceptually family of functions for which the Thurston iterations has a good chances to have a fixed point, we would need to consider the following. So it's the asymptotic area property. It was introduced by Epstein and Rempe in their paper in 14. I think also the relevant discussion was, for example, in this very first paper by Lubitsch and Yeremenko on entire functions. Basically, we consider the following set. Let me draw it. It's illustration. So we consider f a transcendental entire function of finite type from Speiser class. Then we take some. So these are our singular values. So we take some compact set lying outside of all singular values, including infinity. Then if we take its preimage, then we basically obtain different set of asymptotic tracts, also some regular preimages, but let me not draw them. And this set is lying somewhere here between these tracts. And in principle, so we say that f that our function f has area property if the cylindric area of this set measured starting from the disk of so from the circle of radius 1 and towards infinity is finite for any compact set. Okay, so why is this property important for us? Is it because of the following thing? Let us return to this is Thurston's diagram. So it's an F, it's phi, it's a map G, and that is a map phi tilde, integrating the Beltrami differential obtained by the pullback. So what is happening if we if this map phi tilde is just moving our singular values somewhere near the origin, while it's equal to identity outside near to infinity, close to infinity. Then our Beltrami differential, it lives only on this set. So and the maximal dilatation of our quasi-conformal map is bounded by some k. This implies that well, from the asymptotic area from the area property follows that the cylindric area of the set is finite, and by the Belinsky-Teichmüller-Wittig theorem, it follows that, so area property, it follows then phi tilde is conformal at infinity. In a sense, there is a derivative at infinity. So of course, this should be helpful for us because if we consider escaping dynamics, we must have some control in near infinity because there are infinitely many points there. So, okay. However, for our purposes, we need a somewhat more uniform control on what's happening near infinity. Something, on one hand, a bit stricter than just the area property. Let's consider the asymptotic area property. Here, what's happening? We okay. Let me redraw this picture. So we consider our singular values. We draw some neighborhoods around them, and we fix them. We don't change them, and draw some disk of radius rho, and consider this compact set. Then its preimage is again a union of some tracts plus something else, but instead of measuring the cylindric area from just one, so we measure this cylindric area from from outside of the disk of radius rho. Sorry, not inside of the tract, but outside of the tract. So, and it turns out that this area might degenerate. So in particular, we, well, this definition may be a bit confusing. So we say that our function has asymptotic area property if our integral measured starting at rho behaves more or less like if the function nu of rho. But this is the meaningful definition mostly when nu of rho tends to 0 as rho tends to infinity. So let us take a look at the example of the exponential. It's the simplest what we can do. Let me remove this once again. So for the exponential, let us, so this is, okay. So is e to the z, and we have just one singular value, 0, and we, as some fixed neighborhood of it, we draw just a unit disk, and then we draw a big disk around the origin of radius rho. Then, when we take the preimage, what happens? So our compact set would be this infinite strip. Vertical lines with the real part equal to 0, and with the real part equal to logarithm of rho. And again, maybe I didn't draw it very well. So it should be much closer here. Logarithm rho. But when we draw our disk of radius rho and measure the cylindric area of this set outside of this disk, of the strip, then it's going to be very small, because if you rescale, you divide this picture of rho, this the width of this strip is something like log rho or divided over rho, which is extremely small. So in particular, we can say that, well, if you have the exponentials, then the magnitude, then f has the asymptotic area property of magnitude log rho over rho. Well, if you can want to consider more general functions, then, for example, polynomials, exponential cosine, sine, they also have magnitude log rho over rho. And the exponential of a polynomial has the magnitude log rho divided over rho to the degree of p. So, okay. Why is it important? So let's finally formulate some theorem, because otherwise I can speak. So it's rather not the main theorem. It's rather a corollary of a much more general result, but it's easy to formulate it at this point. So here I forgot to write this condition that the function must have definite order. So I had to add it by hands. So let f be the composition of some function lambda, the quasi-conformal function lambda, which is identity near infinity, and with f naught, which is has finite order. It has asymptotic area property of magnitude, for example, 1 over rho to the some epsilon, where epsilon is some constant, positive constant, maybe very small. So then if the following conditions are satisfied, then sigma has a fixed point. So let me talk a bit about these conditions. They are quite simple to be fulfilled. So first, the singular values are not on the orbit of each other, so that we cannot map one singular value to the other. The theory falls apart. So it's just some special case. So each singular value escapes fast. I cannot define at this point what exactly this means to escape fast. But for example, if we eventually have that the image, that the absolute value of the image is bigger than e to the absolute value divided over m is some initially chosen constant, this is included in our definition of fast escape. Sorry. Yeah. And in fact, this type of escape is natural for transcendental entire functions, because usually the point tend to escape with a speed faster than some iterates of the real exponential. So, and finally, there is a condition that in the logarithmic coordinates, there is a positive lower bound on the distances between marked points, so that they cannot be arbitrarily close to each other. So in principle, even if there is no lower bound, one can deal with such cases separately. But for now, let us not do this. So well, you can see it's a pretty general list of transcendental functions for which you have this conditions fulfilled, and then this means that having a map like this, you can always find a Thurston equivalent actually entire function for which the singular dynamics is exactly modeled like here. Okay.
So I wonder, do you know if all those conditions are necessary? Any other counterexample?
No, they're not necessary. It just, okay, I formulate a simplified version of the theorem because at this point, because otherwise I need to introduce like 10 more definitions to state it in full generality. It just was one sort of example. Okay.
But still, do you know some nice counterexamples when sigma has no fixed point?
Actually, no, I haven't seen any example where sigma has no fixed point, at least when we have, well, in this infinite dimensional setting. That's a question how this could be done. So because in all the theory so far I try to work on, so far there always either we don't know the answer, or there is no Thurston abstraction, and there is at least one fixed point. So and this case is exactly a similar one. Okay, so why actually this we might expect this to be the right context to work on. So because we have the following lemma, it's pretty this lemma is pretty easy to prove. So let phi be a map from a unit disk to C, to some domain in C, and let it be quasi-conformal, and such that well, Kz is it's quasi-conformal dilatation at a point Z. Let this integral be finite. Then, in fact, there is some sort of you can provide some sort of Köbi distortion bounds on the behavior of points somewhere, of course, not near the boundary of D, but somewhere on the, for example, on the disk of radius 1/2 or smaller one. So there is one can just prove it pretty easily. This is sort of Köbisch estimate, this Köbi distortion. Okay, and then how does it work? So assume that this function phi is the following: near infinity is almost identity in some sense. It's like or just identity, and assume also that near the origin k of k phi is not very big. Very big, in a sense that k times the magnitude of rho is smaller than 1, for example. And you see that the magnitude is something, for example, for the exponential, it's equal to log rho over rho. So somehow the k would be allowed to be quite big, and but the product could still be small. So and then when we do the pullback, we come here, and then we integrate our Beltrami differential somewhere near infinity. Applying this theorem, we see that near infinity, our resultant function, which integrates the Beltrami differential, near infinity, almost nothing is happening. So that's sort of a source of compactness. Yeah. Yeah.
Second paragraph.
Yeah.
Okay. I have one more question. How do we know that phi prime of 0 exists? You assume that phi is just quasi.
Yeah, I've written it, but it follows from the Belinsky-Teichmüller-Wittig theorem. If this integral is finite, then our function is differentiable at 0. Okay, and there is an analogous statement for the angular distortion, so that the angles also do not change much if you have some uniform bound on the values of this integral given by some kappa. Okay, so let me. So how? Okay, so let me talk a little bit about the more general result, which from which in particular would follow this theorem is the following. So, well, first it's a definition, something that we call a separating structure. Here I must draw some pictures for you once again. So in principle, these properties, except of the property 4, are rather simple. So they are just about our quasi-regular function f. So we have our map f equal to the lambda f naught. So first thing that we have is that we have a big annulus with internal, a big round annulus around 0 with internal radius rho and with external radius q rho, where q is some constant bigger than 1. You will see why we have this formulation on the next slide. So we assume that lambda is equal to identity outside of this inner disk. Next, we assume that our singular orbits that we consider, they do not intersect the annulus. So also our singular values, they are all inside of the disk, inside of the disk 0. And whenever any point of the singular, any marked point leaves this big outer disk, then it stays outside forever. Okay, so there is also a condition. Okay, then there is a condition that n of rho is smaller than infinity. N of rho is basically the number of the marked points inside of the smaller disk. So it basically says that we are not allowed to have we have periodic orbits inside of this smaller disk. Then condition 3 means the following. So Ni and Nk are the last points on the singular orbits I with numbers I and k, which are still inside of the rho. So if it happens that 2 points of such type belong to the same tract, then there should be some so in the logarithmic coordinates, there should be some distance between the images of these points. So it looks Ni plus 1. So they cannot be too close to each other. K and K plus 1. And this we require only for these points. We don't care what's happening further, also for further with coordinates a, I, and k plus 2 or so, they should be just outside of the disk. So, and finally, the condition 4 is sort of more elaborate. So this means the following. Irregularity. For example, if we have 2 tracts, let me draw it. So we have disk rho prime, or rho of radius rho, disk of radius rho prime of bigger radius. Then their preimages is some pair of tracts. The tract T and the tract T prime lying inside of it. What do we do? we say that this pair of tracks is k-regular if when we draw a circle of radius rho prime once again. So we say that the tract T prime is k-regular in T if for any point inside of for any boundary point of T prime which lies in the disk of radius rho prime, we can map it via a quasi-conformal map to the circle of radius rho. And we can do this relative to the boundary of this tract, so that our tracts are not too wiggly, they are not too thin, so it gives some sort of a geometric condition. So let me maybe tell you what follows from the existence of this separating structure. The first thing is that the one thing I should tell you, because I had this theorem for finite order functions, is the following: that if we have the finite order functions and we have tracts which which appear from circles which have some definite gap between them, some epsilon, then this pair is k-regular with k equal to a bound of logarithm rho prime to some degree. So this in particular why the theorem, the first theorem could be proven. So let maybe state the other theorem. It's the following. This works a little bit like the a priori bounds for renormalization. So let f be a function having asymptotic area property of magnitude nu, fix some constant epsilon and an integer m. M is just the number of the singular orbits, or more generally just orbits, because we can mark some other non-singular orbits as well. So there are such constant q naught rho and kappa bigger than 0, which depends only on f naught, epsilon, and m, that the existence of a separating structure with rho bigger than rho naught, q bigger than q naught, and this funny condition k naught squared to the n rho is smaller than k, implies that there is a set, that there is an invariant subset in the Teichmüller space such that the projection of the set to the Teichmüller space based on the marked points only inside of d rho, it is compact, and outside of the disk d rho, our representative phi, the representative phi, they are sort of stable. So there's almost nothing happening near infinity. Okay, so I would like to tell that this result is not only about escaping dynamics, as you see. So in principle, it also covers the case when sigma is defined as a map between different Teichmüller spaces. Because here, well, the projection, the projections, they anyway live in the same Teichmüller space, but instead of living in the same Teichmüller space, there is some funny, it's like nearly identity behavior near infinity. Okay, and then from this theorem, if we manage to consider such phi that near infinity our maps are asymptotically conformal, then we have a compact subspace in the Teichmüller space, and this basically would prove the existence of a fixed point. So I have 3 more minutes, or okay? Yeah, maybe. Okay. So the Okay, yeah, maybe I don't have much time to talk about the spider algorithm. So in particular, so I told you, so somehow how exactly we store the information near infinity. So it's basically there is almost nothing to store because our function is almost identity there. But the thing is that we need some tool to store our information, how exactly our quasi-conformal maps under the iteration behave near the origin. The usual, the standard thing to do this is a spider algorithm. But the problem with the spider algorithm is that it encodes it encodes the information not in terms of the quasi-conformal dilatation, but rather in terms of wiggling of spider legs and the distance between the feet of spider. So basically, the spider legs encode the homotopy information, and spider feet encode the moduli space information. So this is not quite good because we now want to consider general type function f not given by any formula. So usage of spider was easy when we had like exponential or sine or something like this. Then you can sort of bound wiggling of legs or something like this. So there are problems with this approach. So well, as I said, and in principle, we no longer have any invariant spider-like structure for our more general maps. Like, for example, for the exponential, where we could just consider the spider legs to be the standard spider legs to be the some dynamical rays, which model our dynamic. So, in particular, very place. So, the solution is just to consider possible solution would be considered instead of just one invariant spider, which does not exist, just some compact invariant set of spiders. And if we manage to prove that under our map, Thurston map phi, this compact invariant set of spiders is mapping to the same to some other compact invariant set of spiders, but but always the same. Then we also would have some compact subset in the Teichmüller space. And also we need to use a quasi-conformal type of bounds. So therefore, one should introduce a sort of a bit other structure which we call the fat spider. So we no longer, like in this case, we no longer have the body just the point at infinity. Instead of that, we have the body has to be a big disk around infinity. And the legs are just joining the body to some to the feet, which necessarily lie outside of the body. We remember, instead of the wiggling type information for legs, we remember how the dilatation which is needed to move just one feet by not touching the other feet, to move it towards the body. So somehow I don't have much time, unfortunately, to speak about the spiders. So let me skip it. And this could be used to estimate the information near the origin. So let me come to the conclusion, maybe. So we sort of show that entire functions with this asymptotic area property are natural candidates for modeling escaping dynamics, or even more than escaping dynamics. Then so there are some restrictions, sort of in terms of some a priori bounds like style, that under certain restrictions sigma has a fixed point. These restrictions, some of them are the following. So this should be asymptotic area property of sufficiently small magnitude. Then there should be K regularity, which shows that which in a way says that our tracks are not too wiggly, not too thin, are not too degenerate in some sense. And we must have sufficiently fast speed of escape of singular values, because if they are, for example, if they escape with the speed of a polynomial, with the speed of the escape of a polynomial, then the theory would not work. It's not enough, and even for the exponential. And then, so we can construct the invariant subset in the type mirror space with the following form, which is, so our representative maps are almost identity near infinity. So the type mirror metric in its origin is controlled using fat spiders. And K regularity of tracts is used to sort of glue these two regimes. So somehow when we do the iteration, our points near infinity, the first point near infinity, they come to the region near the origin, and this K regularity exactly helps to say that this leg of a spider which appears, the new one, it's not going to have very big to induce very big dilatation. Okay. Yep. Thank you.
Are there any questions or any comments?
Yes. So to clarify, to go straight from the previous slide. So after you obtain all of this and you obtain the sigma has a fixed point, what exactly the conclusion is for entire maps?
Well, the fixed points, they're exactly as in the classical theory, they're associated to some entire functions which exist and model the dynamics or our model quasi-regular map. So it's a way of construction of entire functions with desired singular dynamics, singular infinite dynamics.
Questions, please.
I have a question. I'm sorry I couldn't follow the all the restrictions. So how general is this sum?
Which of them?
Like all of them. If you get a map, because I assume you want to prove that this is good for model.
Yeah, correct.
So the question is, okay, so take a map. I'll give you a map. How big is the chance? I don't know the probability. Obviously, should it satisfy the restriction?
I think, well, intuitively, it feels to me that it's quite big. Asymptotic area property, it feels like it's slightly more difficult to satisfy than just the area property. And for the area property, I think like that 10 years ago, the people even did not even know an example of a function from a Speiser class which does not have an area property. Well, actually there are, but so it's not that easy. So for example, this maps that I know which have explicit form, they in principle have the asymptotic area property. I actually didn't check carefully the structurally finite map. It's given by the integral of a polynomial times exponential to the polynomial, but it feels intuitively that it must have asymptotic area property of sufficiently good magnitude so that to do it with this. I need to check it. So,
Any more questions? If not, we can thank the speaker again.
additional track, just sorry, small remark. So K regularity, it follows from the finite order, as I said. So it's already some